नहीं होता तो
Who are sitting behind, please come forward. Yeah, please come.
मैम आगे IIChe वाले में वो जल्दी से लगा दे, डिजाइन करना सही है तो तुरंत लगाओ। हटा भाई नया अभी जो दो तरीका में वो वाला वही वाला है।
कहाँ
Good afternoon, everyone. I hope you all had a refreshing break. It's now my pleasure to invite a respected speaker to continue with the next session of this conference. Without further delay, I would like to introduce you all with our speaker, Dr. Dolly Sweetlin Jennifer Ma'am, IIT Madras, to kindly come upon the dais and address the gathering. Good afternoon, one and all present here. I'm presenting School of Sustainability from IIT Madras. School of Sustainability, which was initiated in the year of 2024 with strong pointers from UN SDG goals. As you can see, School of Sustainability was built, the complete focus was to bring in academicians, industrial professionals and policymakers and researchers together and have sustainable technologies, sustainable business models and practical policies. So how are we functioning? As an academic, we start with capacity building, as we are expert in how we take the program. We start with capacity building, actionable research, and impact maximization. So here in capacity building, we have developed various courses. We have courses for professionals, because when we were starting with sustainability, all the aspects were already there. So how do we start the change? So we developed courses for professionals. We have different courses that focuses on professionals, executive education program, and we have courses for students. We have minor papers and we have credit-based courses. And then we developed this innovative entrepreneur program for entrepreneurs and people in business. And this particular course that was developed for a Central Auditor General program, which was focusing on ESG audits. So we were trying to build the program around different stakeholders, like different kind of learners, for students, for people in practice, for people who are in authoritative roles. And we are coming up with more courses that is going to cater more towards the sustainable development and redevelopment.
Wow.
So we also have a master's program and MS by research program. Right now we have 6 students, research scholars who are taking up their research program on sustainable interdisciplinary studies. So these are our projects that is currently active. We have 9 projects that are currently active going on and 9 living labs. So we work closely with our student committee, sustainability committee, and we try to take all our projects to enclose with our internal sustainability mission. And these are our new centers that as we speak, sustainability is a very deep and a very wide topic. To start with, we have 3 new centers. We have Center for Resource Efficiency, Recyclability and Circularity and Energy Transition. So we have had different workshops. We had our conference Sustainix last year, and we have hackathon that encourages sustainable startups. And we did have a very good roundtable which focused on problem statements that was actually hindering the sustainable growth among industries and construction companies. So how do we do it as an institution? So we have our strong partnerships with various institutions and industries. So this you can scan and it will take you to our School of Sustainability page, and it will help you to be updated with all the activities that is happening at the School of Sustainability. So School of Sustainability is the major umbrella of multiple centers. As we were trying to work on School of Sustainability, we realized there were so many sustainable ideas that is coming up. So how do we support? How do we encourage? How do we actually make an impact? And then we had, these are our collaborations that we have. We have our centers, we have CTAP, TLC2, we have Center for Circularity, and our center endowments and our project funding. These are all overall projects that is happening at the School of Sustainability. To take more deep, as we speak, we also keep our focus very direct. As an academic institution, whatever the research, whatever the progress that we are trying to talk, when it is as a proper publication, is when we actually can impact towards the change. So we have, from 2024, we were able to come up with these many publications. So this is the hackathon that I was trying to say. So, Climate and Sustainability Venture Studio. So here we were trying to support, we identified how do we encourage sustainable transition among students, among startups. We have a program called IIChe for all. So how do we actually take it to practice? So Sustainable Venture Studios has a program called Carbon Zero Challenge, Ideas to Impact, Stockholm Junior, Sustain Team, and Plastic Circularity Accelerator program. In Ideas to Impact, we encourage students to come with their ideas and we will help them to go to the stage of POC. And we fund them. More than the funding, we give complete technology and entrepreneurship mentorship program. So once they are through this Ideas to Impact, we take them to Carbon Zero Challenge. Again, in Carbon Zero Challenge, it is not restricted only to IIT students, it is for all, it is across India. So people who have their POC come here and develop their prototype. So we help them to go to a better stage of technology readiness. So these two programs are for people who want to go in the direction of startup. And then came the Stockholm Junior Challenge. We realized we've been talking about sustainability, but we are not there in the World Stockholm Junior Water Challenge. So we were the first one to take our Indian students to Stockholm Junior Water Challenge. So here we started it a couple of years back. We had a hackathon for students, school students in the 9th and 10th graders who come up with water sustainability ideas. And the top winner was representing India in Stockholm Junior. And then recently we had our Sustain Team, which is a holistic project on complete sustainability in Tamil Nadu. And then we have Plastic Circularity Accelerator program, which is being supported by Godrej. So, how this Sustainability Venture Studio operates? As well as we support them on the major part of mentorship and seed funding. And then, see, IIT is an ecosystem, right? So we have our School of Innovation and Entrepreneurship coming and supporting them on training and complete entrepreneurship program because deep technology people need how to operate on a business model. So they have experts who are coming, industrial experts who come in and give them complete exposure on pitch deck and complete entrepreneurship journey. And then when they are passed from there, they are put in with IITM Incubation Cell. I think by now everyone would be familiar with IITM Incubation Cell. So there we help them to scale it up as a startup. In pitching, in taking us government tenders, in pitching to projects, more bigger projects. So this is the overall impact of Sustainability Venture Studio. So we have around 125 prototypes, 7 crore is being funded till now, and 1,000 individuals are being trained. 25 startups are in a successful form, and 45 innovations are in progress, and 13 ventures are formed. So this is a glimpse of Carbon Zero Challenge. So here we have different people from different age who have their startup on climate change. And different experts who have been part of this journey in grooming them. So moving from hackathon, when we talk about sustainability, we realized only when we are talking about circularity is when the sustainability come into action, right? So we had a bigger project coming in place under School of Sustainability, a project that was already happening inside School of Sustainability as an independent center. That is Center for Circularity, Center for Resource Efficiency, Recyclability, and Circularity in Energy Transition. And the center was looking for a bigger circularity mission. To start with, HSBC gave us a focus. Right now, everywhere the batteries are there, we have so much of energy transition happening. So we started with energy transition and recyclability. So what is different about this center? We as an institution, we are best in technology. We are best in our patents, and we are best in all the technology that is being developed. So how do we take it to the industry? So this center, we focus on technology. We have focused on pilot establishment. And how do we identify the economic viability of the technology, recycled technology that we have developed. And also, we are talking about supply chain and reverse supply chain. And more, above all, we are also trying to propose the right policy framework that will encourage and make attraction for circularity. So in this center, we are focusing on recycle and reuse of material waste from solar panels and PCBs and recycling from lithium-ion battery. We have started on this. We are planning to go more wider on circularity and also deep in the technology that we proposed. So when we talk about battery waste, as our country is such a populated nation, we will have huge consumption of electronic products. So we are expected to have huge waste batteries very soon. And as already solar panels are very much in existence, we are also expecting to have huge solar panel waste. So we have two projects that is currently going on under the center, where we are talking about deprotonization of e-waste plastics, and the second technology that is completely right now in pilot scale is battery recycling for performance evaluation and scale up. And parallelly, we are also having an audit on lithium-ion battery recycling technology. So when we talk about technology that we are proposing new, only if we audit and we have the record in place how the current technology is more efficient and it is not more consuming water and more energy efficient, is when we can completely arrive at the economic viability of it. So parallelly, we also have another project going on, policy framework for battery and solar waste, and as said, circular economy pricing and recycling industries. When all the 5 projects are going on, we were able to identify some gaps in those 5 projects. And then we extended into more further projects where we realized recovery of metallic nanoparticles were more important, which will be a continuation of those 2 projects. And then we also have a project on reverse supply chain. When we talk circularity, there's a huge gap. After the supply, we don't know what happens to the waste. Okay, it all goes to the landfill. So we wanted to work on the reverse supply chain. So now we are working on a project only for the reverse supply chain of batteries and only PCBs. And then we have a project that goes on extended producer responsibility in lithium battery manufacturing facility. If you can see, the first project is a deep tech project, and these 2 projects is being backed up by our management department team. And furthering, we have next set of 3 projects that works on machine learning enabling sorting and recycling of end-of-life batteries, which is a complementary project to the first project, and green chemistry approach for selective extraction of metals from e-waste and polymer-based sensors. And the last project that we just started was enhancing printability of plastic polymers through rheological characterization. So from our center, we had our first course started as we are responsible of also converting our project into our course to all our students. So this is the first course that is going on, liquid film coating processes and quality assessment. And these are the patents that came under our center. Our center was a new center. It started in 2025. By end of December, we had 2 patents and 2 publications, and 3 more publications due. So through our center, we focused on multiple engagements because as we were talking about actually extending the practice that the development of technology that is happening inside, how do we take it to the industries? How do we talk about it and also look forward in engaging the industry? So we had multiple engagement activities as part of our center. To start with, we had multiple industrial engagements. So we have MOU with startup. We constantly do industrial visit and encourage them to come to our center and understand our pilot lab. And we have visits from industrial experts. As you can see, an expert from Murugappa Group, he visited our lab. So we keep our traction very constant with industrial people because they are the one who's actually working on in a very grassroots level. So we try to connect with them more and more about the technology that is being developed. So furthering the engagement, we also had a requirement how to engage with younger minds about circularity and waste segregation because we had a problem of getting proper waste, not a soiled waste, e-waste. We had that as a problem. So we realized we need to extend our engagement in educating people. So we started an educational program for school children. On a pilot scale, we did it in 3 different districts, in 3 different schools. So we taught the children about how e-waste has to be handled separately and how they have to systematically separate it and take it to the right people. And also we have given a 3-year plan to the school. A school is the communication with us, with the local community. So we have given the school a 3-year plan in setting up a battery collection hackathon for the students and give us data. These many students were able to bring in this much quantity of battery, waste pencil batteries. So this program we look at constantly having the schools in identifying the exact quantity of e-waste that particular population are going to generate. And then we had a program for the waste handlers. So we realized we are talking about different kinds of waste handlers. We have industrial waste handlers, so we did a program for industrial waste handlers, and we did a program with community waste handlers, and also we did a program with informal waste handlers. Informal waste handlers were very interesting. They were part of our community for a long time and we don't recognize them. When we visited their facility or home, we realized they are expert in sorting and segregating. They had very clearly segregated copper, aluminum, PCB, small chips. But the problem is they don't know where to take it to the right. They don't record what's the quantity. They work on their own time frame and they lack in general hygiene. So we are also working on actually connecting the segregated waste that they are collecting and taking it to the right industries. And then we had our first stakeholder engagement. We invited industrialists, we invited experts, we had NGOs coming here, and we had people from Pollution Control Board. So here we had 3 major topics we covered. We spoke about the technology that we developed and what would an industry need to implement the technology in their existing facility and what stops them from doing that. The engagement was such a success that we were able to get very practical pointers from industries, and how an academia can work along with them in the transition phase. And then continuing to our stakeholder engagement, we had one engagement with Industrial Waste Management Association on circular economy framework. So this particular program, we were able to actually break down the circular economy policy under the central government and how 11 committees are formed just to exercise this transition. And as a state, Tamil Nadu came up with another policy, circular economic investment policy, and how our institute, IIT Madras, and our center has an MOU to which what are the achievables we are looking at. So here we were dialoguing with industries who are in textile, industries who are in metal, and what was the problem that was stopping them from looking at the transition. And there was a lot of questions on the funding part for them, and we had strong representation from our IITM team, and also financial institutions were complementing it and saying what are the facilities this policy brings in for the industries who are proposing to change. So this was a very insightful program that we did with IWMA, which was giving an overall framework how industry, academia, and financial institution are going to work together for circular economic change in overall India. So this is I'm just giving a glimpse of the technology that is happening in our center. So this is extraction of critical material from LFP black mass. It has been done in our lab. It is a pilot lab for 10 kg. So generally the black mass we export it to Korea, and then from there it goes to China, and then we buy the material from China. So we are trying to do the same technology in India in our lab. So if you can see how lithium extraction and accumulation device from black mass is happening, that is a very small sample that is being done. Composition on board, we have around 35 to 40% is epoxy resin, and almost 15 to 30% is a non-metal. So how are we actually extracting through de-brominization method? This is just a glimpse. We encourage students to be part of this project as an internship program, also come as a research scholars, because this project is going to take forward to a very greater extent as our center is focusing on taking it to practical application. So this is the lab that we have set. It just initiated in the year 2025 and now it's in full action. So that lab to the left, both the labs are for battery recycling, lithium-ion battery recycling, and the next, this is for solar panel recycling. So, whatever you saw from a hackathon to a very detailed center for circularity, it cannot happen. All these cannot happen without a strong team. So we have a very strong team and very direct focus points. So as a team, we have the whole team is headed by Professor Rajanesh, and he keeps us together with the focus points and what are the mandates that we need to keep in record in whatever the extension or projects that we are looking at. These are the professors who are part of the center and part of School of Sustainability, and the executive team, if you see, we are from different segments. We have an ecologist, we have a sustainable architect, myself I am a sustainable finance consultant. So the team was put together, carefully put together with different people from different walk who can actually work along with the technology experts and work on different projects or curate different projects according to the circular needs. We also have very strong adjunct faculty who work along with all our projects. So these are all the team that we work together, and the team is currently driven by Professor Rajneesh who's with us, and next he's going to give you a nice detailed talk about all the research that is happening. So under our center we are having our next conference in the month July, that is the conference Sustainx Correct. It is on circularity in energy, earth and environment. You can scan, it takes you through the page where you can apply, and we have one-day workshop also on AI in circularity, green economy and sustainable engineering, multi-scale modeling in industrial practices and circularity in energy transition. You can scan, it will take you to the page where you can register. Yeah. Summing up, as we can see, School of Sustainability is a bigger umbrella where we have deep-rooted centers, and as the center keeps working further, it eventually becomes an individual center. How do we do it? We work on the constant collaboration, we work on focusing on strong publications, and also involving students and bringing in more translational research projects. So students may encourage you to be part of this research, apply for internship, and look into the research that is happening under School of Sustainability and under the center. Thank you all.
Thank you so much, ma'am, for your insightful words. To express our heartfelt appreciation, we would like to felicitate our esteemed speaker. May I kindly invite Dr. Shravan Kumar sir to present a token of gratitude to our speaker. Moving forward, I would like to call Shivanshi to introduce our esteemed speaker, Professor Rajneesh Kumar sir.
Thank you, Tanishka. Rajneesh Kumar sir, FNAE, is a professor in the Department of Chemical Engineering at IIT Madras. He is currently head of School of Sustainability at IIT Madras. He is also a board member of Energy Consortium, which is consortium of 14 industries, collaborating on net zero technologies with IIT Madras. In past, he has served as senior scientist at CSIR NCL, Pune, and research associate at National Research Council, Canada. His PhD is from the University of British Columbia, Canada, and Masters from Indian Institute of Science, Bangalore. He has research interest in carbon dioxide capture and sequestration, unconventional energies, process development, and scale-up. Sir is recipient of Shanti Swarup Bhatnagar Award in Engineering Science 2022. Sir is also a recipient of NSCI Scopus Young Scientist Award in Chemistry for the year 2016. He was recognized as highly cited researcher in the year 2018 in engineering. In 2022, Sir received Dr. Y.B.G. Verma Award for Excellence in Chemical Engineering Teaching.
Okay, good afternoon everyone. Am I audible? Yes, sir. Title looks too big, don't worry too much about it. I'm going to keep it very simple. We will try to engage a little bit more, but all of you are sitting all at the back. If you guys come over here, it will be easier for me to interact with you. Moving on. I see in the title over here that you guys are talking about achieving sustainable development goal. So, let's try to understand. Don't worry, I'm okay. I have a little bit of throat infection, that's why I'm talking quite much. So, I'm sure all of you know about UNSDG goals. What exactly UNSDG goals was to identify different topics in which we should become sustainable. There were roughly 17 topics which were identified by United Nations and they were named UNSDG goal 1 to 17. You see different colors, it basically talks about the different UNSDG goals. But what is important for you to understand that even though this goal was identified in 2015 and by 2030 we were supposed to basically improve on most of these goals, the current status seems to be a bit challenging. You see, 17% of the targets have been met, but the remaining 43% of the targets are either stagnant or it is going backward. Okay, so it basically means when we talk about different targets, we mean good, but not necessarily will be able to achieve whatever we mean. Okay, so the question over here is how do we identify the challenges which are supposed to be handled properly before we identify the solutions. And for one has to basically look into different challenges. Today here we are going to talk about net zero, so I'll focus more on net zero. If you look into this particular slide over here, you see in India the share of electricity is mostly dominated by coal. So most of our electricity generation happens through coal. If you look into this slide over here, the consumption of coal has increased over a period of time from 1985 when the consumption of coal was roughly 60 to 65% for total energy production, whatever we are using, either we use coal, we use other resources. For example, you might be able to produce electricity from solar, wind and others, those are renewable energy. So if you look into this, the total energy which we were basically producing, the mix was roughly 60% coal and roughly 40% other form of resources. Today we are 70%, 75% coal and only 25% other resources. So it basically means we have been over a period of time increasing our dependence on coal-based electricity generation. And the right hand side of this particular slide you see there are some other countries. For example, in this data you see Sweden, where the coal products electricity by using coal is almost non-existent. You see over here coal exists somewhere at the bottom. I don't know whether you are able to see it from there. I am not hardly barely able to see it from here. It says coal at the bottom. And all the other sources are hydropower, nuclear, wind. These are the major sources through which they are actually producing their electricity. So what do we see? That if I have to basically achieve net zero, one of the options for us is to, and yeah, there is one more data over here. So in Sweden, if you look into the per capita CO2 emission, they were somewhere around 12 ton. And currently they are at a much smaller number of roughly 5 ton, which is closer to global average, even lesser than global average. So these are some of the data which is available to us, and we have to understand what basically from this data we can learn. One of the options could be to basically stop using coal, move direct from coal to or fossil fuel based energy to renewable energy, and in renewable energy we will have multiple different options. We will talk about some of those. So that is one of the learning which we can see from here. This is the data which basically is a global data which says that at some point of time the total CO2 emission is going to be peaking. Now when it is going to peak, so this data when it was basically published in 2018 was basically kind of assuming that the global CO2 emission has already peaked and it's going to go down from here. But in future, we see today even the current prediction says that the CO2 emission is going to peak at around 2030 or 2035 and only beyond that it is going to ultimately go down. We will talk about some of these. Right now we are just looking at the data. We will try to understand why this data looks like this. Am I audible? Because I am not very comfortable with the voice. Okay. Now let me talk about this particular slide. So we have seen some data. Let me look at little bit more data over here. If you look into the right hand side, or I don't know where is side, yeah, left hand side of your slide, you see there is one data which is mentioned, roughly 41 over here. So that basically tells you what is the amount of carbon dioxide which we are emitting every year globally. Now that 41 is 41 billion tons of carbon dioxide which we emit globally every year. Now with that, it's important for us to understand that if I am going to emit 41 billion tons of carbon dioxide every year to the atmosphere, the CO2 concentration in the atmosphere is going to go up unless and until there is a natural sequestration of these emitted CO2. Either it goes under the ocean or it goes somewhere else but does not remain in the atmosphere. If this entire 41 billion ton is not going to get consumed naturally, then the CO2 concentration in the atmosphere is going to rise. And this is one of the challenge, and this is where the problem of net zero was formulated. What happens if I am going to emit 41 billion tons of CO2 every year and certain amount of this CO2 goes into some sequestration site under the sea or under the earth, still there is significant amount of CO2 which remains in the atmosphere which has been added every year because of anthropogenic activities, that is by human activities. And because of that amount of carbon dioxide which stays in the atmosphere, we see roughly 2 ppm of carbon dioxide increasing every year. Now that basically means if I am going to keep adding these 40 billion tons of CO2 every year, at some point of time the concentration in the atmosphere of CO2 is going to be such that the temperature rise is going to be inevitable. And if you see here, there is one data which says that if I am going to contain the rise of temperature roughly 1.5 degrees compared to pre-industrial temperature, we need to basically ensure that we don't emit more than 250 billion tons of carbon dioxide into the atmosphere from today onwards. Now the question is that if I am going to emit 40 billion tons every year, how long it would take for me to add another 250 billion tons? So that says that we probably need another 4-5 years, or we probably have another 4-5 years, and after in another 4-5 years we will be emitting another 200-250 billion tons of carbon dioxide, and that would basically mean that our global temperature will become 1.5 degrees plus what used to be during the pre-industrial time. So that basically suggests that probably this is the bus which we have already missed, because right now we are not actually capturing any amount of carbon dioxide, or we are not doing much to reduce the CO2 emission. So it means that that bus which we wanted to catch, the bus was to basically reach a destination which is maximum 1.5 degrees beyond what used to be during the pre-industrial time. Okay, and that bus has already missed because we will not be able to catch it. 250 billion tons of carbon dioxide we will add in another 4, 5, 6 years. So that scenario is pretty much gone. Now people are talking about this scenario which you see on this side of the slide. And the scenario over here talks about the day when the global temperature will become 2 degrees beyond the pre-industrial temperature. Now, if you look into this data over here, it says roughly 1000 billion tons credit we have. So the day we add another 1000 billion tons of carbon dioxide into the atmosphere, we are going to reach this target, or this is the destination we will reach. If I am catching this bus today, and if we are working properly, by the time we reach 2050, that in next 25 years, with the current data, whatever we see, roughly 40 million tons of carbon dioxide, it is inevitable that we are going to reach 2 degrees plus the pre-industrial temperature by 2050. And this is the point when it was decided that we should now work on net zero CO2 emission. What is net zero CO2 emission? It basically means the amount of carbon dioxide which we are going to emit into the atmosphere, and the carbon dioxide which is ultimately going to be sequestered naturally by the earth or by human intervention will match. It basically means if I am going to emit 20 billion tons of carbon dioxide from tomorrow, and if naturally 20 million tons of carbon dioxide which is going into the atmosphere is getting sequestered under the seabed or under the sea or anywhere else, then we have achieved the target of net zero. We are not adding any new molecule of CO2 into the atmosphere. Now this is the target. This is the target of net zero which United States says that we are going to reach there by 2050. Okay? And China adds 10 years into it and it says that we are going to reach this target by 2060. And in India we have added another 10 years and India's target is to reach there by 2070. Now 2070 is at least 2 generations later. My generation is seeing it, your generation will see it, and probably your kids' generation will also see it, and then they will reach by 2070. So we have identified a number which is way far in the future, assuming that we will be able to reach there by 2070. But just giving a target does not mean much. We have to understand what are the challenges which we are going to face if we have to achieve this target. Okay, so this topic or this presentation is mostly about these challenges. Do we understand our challenge is something which I am going to talk about today. So roughly, if you see from this slide, we say that roughly 50-60% of the CO2 which we emit has to be somehow avoided. Now how do we avoid this CO2 emission? There are two options with us. We saw from the previous data is that either I move from not using fossil fuels for all our energy need, that is coal, oil, natural gas, all of that, or the other option is that if I am still using it, I should be able to capture my carbon dioxide and put it back under the earth. Why? Because right now all the carbon is coming from under the earth. We are digging all our fossil fuels, we are burning it to get the energy, but the main product which is carbon dioxide, after burning of coal, the main product is carbon dioxide, not the energy. Energy is the byproduct which we utilize. The main product we release to the atmosphere. Okay? So this is the one-way path. Even 200 years back, it was known that if we keep doing it, some point in future we will have this challenge. So we have basically estimated it already that this one-way path is not going to work. We will have to close the loop. How do you close the loop? The only way you close the loop is by capturing the carbon dioxide which you have already emitted and put it back under the earth so that you are able to basically close the loop. So what are the two solutions we talk about for net zero? One is either we move away from fossil fuel based energy and start using renewable energy that would reduce the CO2 footprint in certain period of time. And the second option is to basically capture the CO2, utilize it or sequester it, maximum whatever we can actually do through our human different technologies which we basically come across. So now these are the two options. In future, I am sure both the options will ultimately be utilized simultaneously, but we will today not talk a lot about renewable option that requires a different day. Today we will mostly focus on carbon dioxide capture. So we will talk about it maybe little detail, but it clearly shows that even if I have to capture some 500-600 billion tons of carbon dioxide in next 25 years or 30 years, where all this capture is going to happen. Each of the industries we talk about are going to be different, very different in terms of the way the interventions are going to work. For example, if I am going to talk about electricity generation, you saw very clearly that if we move from coal to solar and wind, it's not a big deal. We will be able to actually convert most of our CO2 emissions, or we will be able to avoid most of our CO2 emissions in some period of time. Okay? So electricity generation, which is in India currently roughly 70 to 75% dependent on coal, has to completely move out away from coal to green sources, which is renewable, which is written over there. Okay? And if I am able to do that, roughly 200 billion tons of carbon dioxide can be basically avoided in next 25 years. The target has to be for next 25 years. Okay? Part of the CO2 emissions which comes from electricity generation has to remain CCUS, because many places you will not be able to basically use solar and wind. So there you will have to go with fossil fuel based energy, and with that you will basically implement CCUS, and this is how you are going to basically make that process CO2 neutral. And obviously energy efficiency, which is shown in that orange color. And nuclear energy is one big chunk in power generation. There is some challenge in nuclear energy we will not talk about today, but this is the blueprint to decarbonize electricity generation. And you see this, if I am able to achieve that, roughly 300 to 350 billion tons of carbon dioxide emission could be avoided in next 25 years just by focusing on electricity generation. Remaining 350 billion tons has to come from other interventions, which is going to be in industrial sector. What are the industrial sectors? We are talking about the steel or manufacturing, cement manufacturing, aluminium manufacturing. Each of these processes, pretty much everything which we produce requires energy, and currently it is being done by fossil fuel. So there you can see it's not very easy for you to basically replace in next 25 years those fossil fuel based processes to non-fossil fuel based processes. So there you clearly see that there is a much larger portion of CCUS intervention there. Okay, most of these industries will operate like that, because investment as recent as last year, in last 5 years, which has been done in steel industry or cement industry cannot be stopped today. It will keep producing for next 25-30 years. And it basically means that you cannot do any large scale intervention in those industries. So there you will have to rely on retrofitting. Retrofitting basically means that you will have to approach these challenges as capturing the CO2 and sequestering it. The orange line over there is that obviously efficiency. Efficiency increase is always better, but I don't know how much we will be able to achieve that. But the problem is that in industry we don't know what ultimately we will do. The target is to basically decarbonize industries by 150 billion tons in next 25 years. It's going to be very difficult. Industry decarbonization is not an easy task. Similarly, you have transportation, buildings and other areas. We will not talk about it today. So the point is that, 2 points again. Now if India has to completely move from fossil fuel based electricity generation to renewable electricity generation, we need to again look at the data, how we have performed in past. And if you look into this particular data, it shows that all the renewable energy put together, hydro, solar, wind, biomass, waste, geothermal, wave and tidal, in 1985 we were having roughly 30% renewable. Today we have only 17-20% renewable. So it basically means in last 30 years, 40 years, we have actually gone backward. So that clearly shows that if I keep talking about, it's not that we have not been talking about renewable. In last 30-40 years, we have been keep talking about renewable. We have been talking about solar, we have been talking about biomass. We claim that we have plenty of biomass to supply all our energy need and all, but still this is the reality. So what it tells you, economics and behavior are two different things. Okay, you can't really change something just because you have been talking about it. You'll have to have the right process to change some of those. So it clearly shows that if you really have to decarbonize your electricity generation, it's not going to be very easy. It's a very difficult task. And because of that, you see the CO2 emission from one country like India has increased significantly, and currently we emit 3 billion tons of carbon dioxide every year. How much we emit? 3 billion tons every year. Okay? World over, there is 40 billion tons of carbon dioxide emission every year. In India, we emit 3 billion tons every year. We are third in the list. Okay? The first is China with 11.5 billion tons of CO2 every year. Second is United States with roughly 5.5 billion tons of CO2 every year. And in India, we emit 3 billion tons of carbon dioxide every year, which is increasing at the rate of 5 to 6% every year. What is the rate of increase for India? 5 to 6% every year. With this rate, by 2040, we will become the second largest CO2 emitter. And by 2050, it is proposed that we will become the largest CO2 emitter. The pace at which China is decarbonizing their industry and the pace at which we are carbonizing our industry is stark. Last year, we have consumed 8% more coal compared to the previous year. So if I am consuming more coal, it basically means our CO2 emission is going to go up. There is no other way out. Okay. However, the good news is we have been able to replace significant amount of our electricity demand from fossil fuel to non-fossil fuel based. We will talk about some of those numbers in next few slides. But the point I was trying to make here that if you see right now India emits roughly 3 million tons of carbon dioxide every year. And with this data, let me tell you, if I have to even reduce 50% of carbon dioxide every year, let's say not tomorrow, in 25 years time, that basically means we will have to invest significant amount of money for doing something like this. Okay? So now let's talk about two things. As I was telling you that renewable, I am not going to talk much, but little bit I will certainly give you some example. Let's talk about renewable. It's not that as soon as you move from fossil fuel to renewable, everything becomes green or you will not emit any carbon dioxide. Let me help you with some maths. Okay? All of you are chemical engineer, I'm sure you should appreciate the data over here. You look into the data. If I have to produce hydrogen, we will talk about why hydrogen is very important. But if I have to produce hydrogen, green hydrogen, 1 kilogram of green hydrogen would require 55 units of electricity. Okay, you will have to split water by electricity. You do electrolysis process, you will split H2O to produce H2 and O2. If I am going to split H2O by the best technology possible today, I consume 55 units of electricity, that is 55 kilowatt hour of electricity. Okay, so I consume 55 kilowatt of electricity to produce 1 kilogram of hydrogen. And if I have to transport this hydrogen 400, 200, 500 meters, only 100, 200, 500 meters I am talking about, not kilometers, I would consume 10 to 15 kilowatt of electricity. Storing and transporting it only for that small distance. I am not even talking about transporting it to kilometers. Okay? So that basically means that we have already consumed 65 kilowatt hour of electricity minimum. Now what do I do with this 1 kg of hydrogen? If I produce back electricity from this 1 kg of hydrogen, I will only get 20 kilowatt hour of electricity. So what does that mean? That our efficiency is not much better here. I have consumed some 70 kilowatt hour electricity and I am getting back only 20 kilowatt of electricity. So that basically means I am losing roughly 50, 60 kilowatt hour of electricity in the process. That is something which one has to always understand. It's not that this, and each of these processes when we talk about is not 100% efficient. It basically means that if I have to install a capacity of 1 kilowatt hour, I will only produce 0.3 kilowatt hour out of it. It basically means I will have to install 3 times. Please understand what I am trying to make here. If my need is 1 kilowatt hour, I will have to install for 3 kilowatt hour. Why the installation is important? Now you see here, why we talk about hydrogen? We talk about hydrogen because hydrogen fits quite well with solar energy. Solar energy is only available during the sunshine hours, which is on average roughly 5 to 6 hours a day. If you talk about all year-wise average, it does not have more than 20% plant load factor. It basically means if I have installed 1 kilowatt hour, I will maximum produce 0.2 kilowatt hour. Okay? So for 6 hours a day, I might have sunshine. This is when my electricity will get produced. For the remaining 18 hours of the day, I need to store this electricity. Today we don't store any electricity. So what do? I install 5 times. Okay? use one portion of it, and the remaining 4/5 portion I store so that I can use it for the remaining 18 hours a day. So what do I do with renewable energy? Where is the challenge? You see, I am installing 5 times solar panel. I am installing 3 times hydrolyzer because the efficiency is very poor there. So the installation requires significant amount of investment. Today we have roughly 250 gigawatt hour. We have roughly 250 gigawatt of installed coal-based power plant in the country. How much? 250 gigawatt. That is typical our consumption. That is our yearly consumption. We also have roughly 260 gigawatts of installed renewable energy in the country. How much is that? 260 gigawatt. The installed renewable power electricity is actually higher than non-renewable. But then how much do I get from there? We hardly get 50-60 gigawatt from that 260. That's the kind of plant load factor a renewable power plant will typically have, roughly 20%. So that basically means if I have to replace all my 250 gigawatt of electricity, I will have to multiply it by 5 times for the installed solar capacity. Then I will have to also now calculate how much hydrogen I will have to basically produce. There, if I have to start installing electrolyzer with this efficiency, I will have to start 3 times what I need actually. Or I will have to go to batteries. If I am going to batteries for storage of this electricity, solar panel runs for 20 to 25 years. Batteries does not run more than 5-6 years. So there also for an entire solar panel lifetime, if I am looking for installing batteries, I will have to install batteries 3 times in that entire solar panel lifetime. Why this installation is important? This installation is important because we are talking about net zero carbon dioxide. And I'll tell you what is this net zero carbon dioxide in the next slide. I'll move on to, since we are chemical engineers, we have some of these. See, solar panel consists of multiple molecules. Okay? And this is the reason why I had it over here. You see, a solar panel will require you to have multiple different elements. You would need how much silica you would need metal, you are going to have huge amount of other processing problems. All of these will consume electricity. For example, silicon, which is the most important part for solar panel, requires you to process it at twice at 2000 degrees plus. Okay? So the silicon which I am going to basically use in the solar panel, which is part of the solar panel, comes from an ore which requires to be processed at 2200 degrees centigrade so that you can purify that ore and it becomes 99% pure silicon. That is called metallurgical grade silicon. Okay? Now you take this metallurgical grade silica, multiple processes basically will accumulate lot of this metallurgical grade silica. Now you are going to basically convert this metallurgical grade silica into electronic grade silica, which is 99.999999% pure, 99.79% pure. Okay? That requires you to basically process it again at 2200 degrees centigrade. And at this time, this process happens in a vapor condition. Basically, it's a gaseous reaction. So typical of any gaseous reaction, per pass conversion is hardly 9-10%. So you will have to basically recycle it 10 times. So this 2200 degree operations runs at really long period of time, and ultimately your pure silica 99.99999% gets deposited on the walls of this reactor. In vapor phase, the reaction happens and the walls of the reactors are kept cold so that these crystals can form on those cold surfaces. You know what do they do after that? They break the entire reactor. Every time they have to break the reactor to get the silica. That's the only process which is there right now. It's a complex process. It runs at 2200 plus degrees at very high temperature. And how do you get that 2200 degrees today? All of that comes from fossil fuel. Okay? So if you look into a simple maths, if you go and do a simple literature search on Google, you will find that a solar panel should be able to pay back the CO2 footprint in 1 year to 1.5 years time. Okay? So it basically means the CO2 which got emitted during the formation of the solar panel will be able to pay back that CO2 in 1.5 years of its operation, because during 1.5 years it will produce electricity. That basically means the electricity which the solar panel is going to produce will avoid a coal-based power plant. So you will calculate how much a coal-based power plant would have produced carbon dioxide during this 1.5 years period. So if you basically do those calculations, you will realize that a solar panel will pay back its CO2 footprint in 1.5 years time. Let's say it is 1 year only. But where is the challenge I was telling you? That if I have to install 5 times solar panel for my requirement, this 1 year will become 5 years. Okay? Now, what did I tell? That I will not only install the solar panel, I have to basically store all the electricity in excess which I have produced during the 6 hours of sunshine, so that for the next 18 hours I should be getting that electricity. Then I'll have to also see what would be the CO2 footprint of the batteries, or what would be the CO2 footprint of the electrolyzers which I am going to basically produce for hydrogen generation. So there I am going to add another 3 years. So how much it became? 8 years. Now I have not even added the recycling actually. Now at the end of the 20-25 years period, the solar panel I will have to recycle. So I have not added. So what do I mean? I mean to say that as soon as I am putting a solar panel, I am not becoming net zero. I am becoming net zero only 8 years, 10 years down the line. Not before that. So that basically means that if I have to start doing some intervention for my CO2 footprint, which I have a target in 2050, I'll have to start now. If we don't start now, then by 2050 we will not have enough net zero potential. Okay? So that's the first thing which I wanted to talk about. And this typically is mentioned over here very clearly in this particular slide. If you look into this particular slide, it says very clearly that if I am going to produce electricity, see per terawatt hour is clearly written there, by solar, then roughly 16,000 to 17,000 tons of material has to be processed if I have to produce 1 terawatt hour by solar panel. But if I am producing 1 terawatt hour by coal or natural gas, we only process roughly 1,000 tons of material. What is the difference? The difference is nature has cooked the raw material currently what we are using. Currently we are using coal, we are using oil, we are using gas. In last millions of years, nature has cooked this material for us. During this cooking process, all the CO2 which got emitted has already gone into the atmosphere. While I am basically using some of these, I am not basically emitting any carbon dioxide for cooking. Okay, I am just using it. I am using the carbon part of it, and when I am using it, I am emitting CO2 for the energy. But when I am going for solar panel, or if I am going for wind turbines, I am cooking the material now. Because any material which I am creating, I have to cook it today. I am cooking a polymer, I am cooking a silicon panel. All of these being cooked today by me. When I am going to cook it, I am cooking it again with the same fossil fuel. So I am emitting a lot of CO2. So this CO2 comes out as an embodied carbon dioxide, and we did, right now we did a calculation and we see that cooking a solar panel emits carbon dioxide for next 8 years, 9 years already. Yes, once the solar panel has started producing electricity, the CO2 emissions are not there. But the cooking part itself has emitted 8 years of electricity. Now that is something one has to always understand, and this is what this particular slide tells you. That if I am going to talk about a renewable energy, I need to basically worry about the amount of material which I need to process today. It will generate jobs, no doubt about it. And this is the best part about it. Because all those electricity which India has been 250 gigawatt of electricity which India produces today was not done in 10 years. It took us 70 years to install 250 gigawatt. All the jobs which were generated due to this 250 gigawatt of power plant installation has gone. Today, a power plant which I will tell you, a power plant which used to run 2000 gigawatt, produce 2000 gigawatt, used to require some 5000 workers. Today, hardly 200 people are needed. So these jobs are already gone. Now when I am moving from fossil fuel based to non-fossil fuels electricity generation, good part is that we are generating a lot of jobs. It's going to be good for the young generation which I see here today. But then whether it is net zero, we have to question that. Okay, it is only the solar panel net zero only after 8-10 years. This is what I was trying. Moving on. So what I was trying to mention over here that obviously moving from non-fossil fuel to non-fossil fuel is difficult. As we saw the data from India, we had 30% renewable energy in our electricity mix in 1985. Today in 2025 we have not even 20%. So that basically means after all the talk of renewable energy, we have not been able to improve it. The second challenge with renewable energy is that the day you are installing it, you cannot become net zero. It will take some 10 years for you to become net zero. Whatever renewable energy you are going to implement does not matter. Since you are cooking new material, you will emit lot of CO2 and will only become net zero in 10 years time. So that is the message for renewable. What is the message for CCUS part? So CCUS part is something which I am going to cover little quick for me to finish. So I hope I will be able to finish it in next 10 minutes. See, when we talk about CCUS, one has to please understand that CCUS is a three-step process. The first C is carbon dioxide capture. Okay, what is capture? As a chemical engineer, you will understand capture is a separation process. We are trying to separate carbon dioxide from the other associated gases. Okay, and as a chemical engineer, all of you know, separation process are the most intensive process in any processes. Okay, the unit operation of separation is the most energy intensive process. We talk about how do we separate typically in chemical processes by distillation. That consumes the most of the energy. But separating two liquids which are intermixed with each other is even much easier. And that itself is also energy intensive. Here we are trying to separate what? We are trying to separate two gases which are intermixed with each other. It's not that easy. Okay? So, if I have to separate carbon dioxide first, there are two places where I will separate it from. Either from the location where I am emitting it. Where I am emitting it, it's at higher concentration. If I am emitting it at flue gas point, basically where the electricity is being produced by burning coal. So when we burn coal, there are multiple challenges when we burn coal. Coal is a solid and the oxidizer is a gas. So how do we do that? Solid will have millions of molecules in a small volume. And an oxidizer which is oxygen, which is not pure, which is mixed already with 80% nitrogen, is there in a very minute amount in a small volume. So what do? The first thing we do is that we pulverize coal. We make a very small particle of coal. So from multiple millions we come to few millions. We can't do better than that. That's insanely energy consuming if I basically grind it finer. So we basically come from multiple million molecules to few million molecules, but we still have one gas molecule coming and interacting with millions of carbon molecules. What do? We basically pressurize the gas. Okay? Instead of using pure oxygen, anyway we use air. So we somehow pressurize the gas. What is the end result of all of these? The end result of all of these, the gas which comes out after combustion is highly dilute. For example, 9%, 10% carbon dioxide and remaining nitrogen, oxygen, and some other SOx is there. So what are we trying to do here? I am trying to separate one molecule of carbon dioxide from 9 molecules of nitrogen. Let's say all the other gases are represented by nitrogen. So what do I do here? Here when I am going to capture CO2 from point source, there I am capturing 1 molecule of CO2 from 9 molecules of nitrogen. That's the process as a chemical engineer we are trying to do. If we don't catch it over here, then it will go to the atmosphere, and it's even a big problem. When it goes to the atmosphere, what is the concentration of carbon dioxide there? Any one of you, what is the concentration of carbon dioxide in air? 426 ppm as of today. Okay, so that basically means I have 1 molecule of carbon dioxide and how many molecules of nitrogen? 2500 molecules of nitrogen. How many? 2500 molecules of nitrogen. Now as a chemical engineer, what is your job? Your job is to identify this 1 molecule sitting around this 25. You have assumed there is a one guy sitting here and surrounded by 2500 other students. First challenge for you would be to identify that person. And this person is at high temperature, let's say at room temperature. This molecule is having huge amount of thermal fluctuation. That basically means that this person is running around and there are 2500 other persons running around this person. Now what is the challenge? The challenge is that I need a material which will be able to identify this particular guy and will be able to catch that guy. And out of 2500 other molecules, can you imagine how difficult is this task? So the challenge here at point source capture, where there is 1 molecule of CO2 surrounded by 9 molecules of nitrogen, is much simpler. But if it goes to the atmosphere, if you have to catch CO2 from there, you can imagine how difficult that going to be. And this basically is reflected very easily into the cost of CO2 capture. The cost of CO2 capture over here from the point source is roughly $50 per ton. Now please remember the numbers. $50 per ton. Okay? How much CO2 we emit in India every year? 3 billion tons. Okay? Please look at the number. Now if I am not catching it here, which was simpler for me to do, I let it go to the atmosphere. If I am going to catch from there, you know what is the cost of CO2 capture directly from the air? $200 to $1,000 per ton. Obvious, as a chemical engineer, there is no big deal. We know that if it's much dilute, ppm level dilute, if I have to capture it from there, it will be very expensive. No doubt about it. But then this is what we are trying to achieve in carbon capture, utilization and sequestration. Please understand that. See, the big problem is when in early 60s, when power plants were built, people said, no, it's too expensive to separate oxygen from nitrogen because it is part of the air. Only 20% oxygen is there, 80% is nitrogen. Why to basically separate it and do the combustion? Let's do the combustion in air itself. It was too expensive, it was thought that it is too expensive to increase the cost. Today, the situation is such that we are ready to separate 400 ppm CO2 from the air. Can you imagine? But anyway, so the point is that CO2 capture is happening here. But what we are trying to achieve? Forget about the cost. What we are trying to achieve? We are trying to achieve net zero. And what is net zero? I have captured the CO2. Now you see, when we talk about capturing CO2, what did we say? We said that it's a separation process. And you know any separation process will be energy consuming. So when a process is energy consuming, as we have been discussing in last half an hour, it will emit carbon dioxide. Okay, it cannot happen without CO2 emission because we have been only knowing using how to use fossil fuel energy to do any process. So now the question is, I am going to do the calculation not by the cost. Cost will come later. What was the target? The target was to achieve net zero. So what is that target? If I am going to capture 1 molecule of CO2 from here, the process of CO2 capture plus the transportation of that CO2, plus the sequestration of that CO2, the process of transportation and sequestration, everything put together should emit less than 1 molecule of CO2. Otherwise, how you are net zero? You are not net zero. You say that I work on carbon dioxide capture, but you have captured 1 molecule of CO2 and in the process you have emitted 2 molecules of CO2. So what is the use? That is not the use, because what was the end goal? End goal was to achieve net zero. This is where most of the technology fails. And this is why I was talking about on the previous slide that we target some of those things. But we see that in 97% of the cases we are not able to achieve the target. Because we don't plan it properly. If you look into this is the first challenge and this is the first red flag you will see in CCUS. When we talk about carbon dioxide capture, we have to understand how much energy is needed. And since we are running out of time, I will focus on one point which will basically tell you the challenge. Let's move on into all of this. We have discussed this. This is the point which I wanted to talk about. Now let's talk about this slide. We will spend some time over here, then we will move on. The first challenge which we have with CO2 capture is this. See, today we have many solutions for CO2 capture which is scaled up for full plant scale. Don't worry about that. There are many technologies. And one of the major solutions people talk about in industry is using certain amines to capture carbon dioxide. What is this process? The process is very simple. Amine being a basic molecule, carbon dioxide being a Lewis acid, will react with each other and then form a salt. Okay? So if I have a mixture of 10% CO2 and 90% nitrogen, if I am going to pass this mixture to a liquid which has amine in it, all the CO2 will preferentially react with amine and CO2 will become a solid carbamate and the nitrogen gas will come out. Done. Okay? One step is done. What is the second step? Second problem is that amine cannot be produced from thin air. So I need to generate amine every time I have to capture. And how much capture? 3 billion tons in India, 40 billion tons worldwide. Please understand the numbers are very important over here. It basically means I will need huge amount of amine. So this amine has to be regenerated. So what is the problem? Now the problem is that the carbamate has formed. Now I have to break it down. Now this is a question of how much energy I will consume. So now if the concentration is 10%, I will go for some molecule which will strongly bind with CO2. If the concentration would have been 50%, then I would have gone with a molecule which is not strongly binding. So if they don't bind strongly, then regeneration will be easier for me. But now what is the challenge? The concentration is only 10%. So I will have to go for an amine which will strongly bind with CO2. But now since it is strongly bound with CO2, now I will have to supply a lot more energy to break it down. And that increases the temperature at which it has to be done, the time for which I will have to cook it, and all of these, as I was telling you, comes from the same fossil fuel which I am burning. So that will have a CO2 emission. So now if you look into this process, CAN-SOL, which is basically the most commercially viable amine mixture which is currently used worldwide, is a mixture of amine, proprietary with cell. They basically sell it to everyone and they do all the process. Consumes 2 gigajoule of energy for 1 ton of carbon dioxide capture. Now this is 2 gigajoule is a very optimistic number in people who work in this area. Typical numbers are 3 to 4 gigajoule. 2 gigajoule is a very optimistic number. But let's look at 2 gigajoule number. How good is this number? Now what it says that if I am going to capture 1 ton of carbon dioxide by using CAN-SOL, which is a commercially viable, commercially scalable solution running across the globe, will consume 2 gigajoule of energy. So the first question as an engineer I will ask, how much electricity was generated to produce 1 ton of carbon dioxide? Because I have to retrofit it in electricity unit, no? So I'll give you a number. Typical numbers are in India or across the globe, 1 unit of electricity, which is 1 kilowatt hour, if you produce, you will generate 800 grams of carbon dioxide. For simplicity, let's say this is 1 kilogram of carbon dioxide. So what does that mean? If I am generating 1 unit of electricity, I will generate 1 kilogram of carbon dioxide. What is 1000 kilogram of carbon dioxide basically mean? If I have 1000 kilogram of carbon dioxide, basically mean I would have generated 1000 units of electricity. What is 1000 units? It is 1000 kilowatt hour. Can I convert it into joule? Very easily. I will convert kilowatt into watt by multiplying it with 1000, and I will convert hour into second by multiplying it by 3600. So I will produce 3.6 gigajoule of electricity and produce 1 ton of carbon dioxide, and if I have to capture carbon dioxide, I will consume 2 gigajoule from there. What does that mean? That means a 500 megawatt power plant will become 200 megawatt power plant if I have to capture CO2. This is the best process available today. Now this is one of the challenges we talked about. I will stop here on this topic. There are ways to do it though. I will tell you there are ways, we will talk about it later. The solutions can come later. We will focus on the challenges now. The second challenge I will talk about, I will skip some of those things. Ultimately we will go to the slide which actually matters. Yeah. The first challenge we talked about was, by the way, how much time do I have? See, looking at me, everyone is worried. Do I have 5-10 minutes extra? 5 minutes is okay, fine. Okay, so we talked about the challenge in terms of energy. We don't want to consume 300 megawatt out of 500 megawatt, no? That is one challenge. The second challenge is here, which is actually a bigger challenge, the kinetics. Because in chemistry, people don't understand kinetics. Since we are in an audience where most of us are chemical engineers, let's try to understand the kinetics. See, kinetics is a bigger problem. And if you're not an engineer, you will not think it this way. Now let me tell you, the largest CO2 pilot plant, CO2 capture pilot plant in India exists at a capacity of, you know what? 20 tons per day. A mere 20 tons per day. This pilot plant is in a place called Vindhyachal Super Thermal Power Project. This place is called Vindhyanagar, which is there in MP, some area around Singrauli. I am sure many of you would be able to connect with Singrauli, which is a coalfield area. So let's try to understand the maths of this plant. This plant will produce at least 3000 gigawatt hour of electricity. Okay, 500 megawatt electricity, let's say, is 1 unit out of 6-7 units they have. If I am going to look at the amount of CO2 which comes out, the kinetics, please understand that. The kinetics tells me that if I am going to produce 500 megawatt of electricity, I am going to produce 500 tons of carbon dioxide per hour. That basically, if I am going to convert it into second, it turns out to be 0.15 tons of carbon dioxide per second. Why I am talking about it? Let me tell you. If I am going to capture CO2, I can't just catch the CO2 molecule. I need a material which is going to be synthesized. We talked about amine, or we talked about metal organic framework, or geolites, all of these. But each of these material has to always understand the rate at which it has to be doing, because I am going to retrofit it. If 500 tons of CO2 is coming out every hour, I need to at least capture 250 tons, if not 500, so that I can claim that 50% of this material has been captured. So, if you look into this data, I am bringing in second because the literature, the scientific literature will only record data in seconds. Okay? So this is why I am bringing it in seconds to 0.15 tons of CO2 per second. So you will now go and find in literature how many materials are there which are reporting this kind of data. How much material they can capture, how much CO2 they can capture in per gram of material per second. Okay? So that's the kind of data you will go and find in literature, and you will realize the numbers are, that is an error, 0.2 to 0.25, but roughly 0.009 tons of gram of CO2 per gram of material per second is the data you will see. That basically means that the material which you have designed, the best of the material which you have designed today can only capture 0.009 ton of carbon dioxide per gram of material per second. If I am going to just go from gram to ton, scaling up without losing much, I can say that okay, by doing this I will lose 10 times, but in this calculation I am only losing half of it, let's say. You will basically need 16 tons of the material. Actually, so you can say that 32 tons of material will be needed. And since the capacity has gone down by half, I am also assuming that the kinetics will go down by half, but in reality it will go down by 10 times at least. but it goes down by half. It basically means that 32 ton of this material will be able to capture 50% of my CO. Let's say this. How do I pack 32 ton? Now 32 ton has to be packed in a 20 meter by 3 meter reactor. In 1 second, 0.15 ton has to get exposed. See, this is the rate at which the kinetics is very important. How do you design something like this for capturing 50% of your CO2 coming out from a power plant? It's not that easy task. So it's not only about the energy which we are consuming is significantly high currently, it's also the rate at which we are actually consuming them is not sufficiently high enough. So the focus has to be on all of these. How do we basically ensure that the total energy penalty comes down? How do we ensure that the rate at which this CO2 capture is happening goes up? And the most important part, how do we ensure that the regeneration losses are minimal? Because if I am not able to reduce my regeneration losses of material, then my CO2 footprint will overtake. For example, I will tell you, now you talk about 0.00 tons of CO2 per ton of material per second. If a metal organic framework, typical metal organic framework which will go in the market, this year it got Nobel Prize. What is the CO2 footprint of such material? If I am going to produce 1 kilogram, anyone can have any numbers in your head? Minimum 200, 300 kilograms. If I am going to produce 1 kg of these materials, I will produce 200, 300 kilograms of carbon dioxide. So now do the ratio of this and see whether the CO2 which is going to come out from this metal organic framework formation, whether that material will be able to capture its own CO2 or not. That's the first question one has to ask. And then only you will see that the material is capturing some other CO2. So this is something which people has to always keep in mind when they talk about working on CCUS. Some of these materials are currently being used in market. I don't want to focus too much on that. We will show some of the solutions which we have found in our lab in IIT Madras. I'm not going to show anything in detail. We will show you some of these setups which we have basically done. These are all done by our students. From all the places, we start from molecular level studies, we go to lab scale, and then we go to pilot scale. So it's done at different scales. This is one of the process which we have already delivered to L&T, is a direct air capture unit, which is currently, I'm sure they have already implemented some hundreds of these units for the requirements which they have. There is one more topic which I want to touch upon, which I have not touched upon so far, is we talk about carbon dioxide capture and then we say that we will convert it into some chemical and it solves all our problems. This is one thing which I will tell you, whenever you are trying to utilize carbon dioxide, you are not utilizing carbon dioxide, actually you are trying to somehow ensure that hydrogen is utilized, because any utilization of CO2 requires hydrogen. We are always converting a carbon dioxide into a hydrocarbon. So how do you get hydrogen in CO2? There is not hydrogen, no hydrogen there. So I'll have to add hydrogen into it. Okay, so please be aware that hydrogen addition is not an issue. You see here, urea production is one of the CO2 utilization approach. You can produce urea, it's a CO2 utilization. But where is the devil is in the details. The devil there is that urea production required 12.5 gigajoule per ton of energy. CO2 capture is only 2 gigajoule. So it's not the CO2 capture which is creating a challenge here. How do you get 12.5 gigajoule energy without consuming fossil fuel is the question which one has to worry about. Not about this 2 gigajoule, which is not even 10% of the total requirement. So this is something which one has to always understand. The chemical engineer, we have to focus on the process, not on where the CO2 is coming from. There is another challenge over here. When we talk about producing something like methanol, let's look into the simple data here. Methanol from utilizing captured carbon dioxide, please understand it's a very expensive molecule. When we talk about $50, the cost of CO2 capture, roughly 5 rupees per kg is the cost of carbon dioxide. What is the useful component there? Carbon. How much is the carbon? Only 25% or 20% of that. It basically means the cost of carbon is 5 rupees per kg if you are using the carbon in your methanol from captured CO2. What is the cost of carbon available in India today? Last year, 1 billion tons of coal was sold by Coal India Limited. 80% of that was sold at 1 rupees per kg. So now you are saying that I will use 5 rupees per kg carbon for producing my methanol. You can use it. But then what else you need? You need green hydrogen, which is currently at 400 rupees per kg. So now you add 5 rupees per kg carbon and 400 rupees per kg hydrogen. At what cost you will produce methanol? Minimum it will be 80 rupees per kg. Who is going to pay for that? That's the question one has to always understand. It's not only about energy as well, it's also about the cost. How do you do it? That's a separate challenge. Fine, I think with this I am going to stop. I will not focus too much on this. The second part was CO2 sequestration, which I believe can be done later. Thank you very much. If there are few questions, one or two, I should be able to take it, mostly from the students. If you have no question, then fine, you can always talk to me later.
Thank you so much, sir, for your enlightening words. To express our heartfelt appreciation, we would like to felicitate our esteemed speaker. May I kindly invite Professor Devnani, sir, Professor Rathore, sir, and Professor Sastry, sir, to present a token of gratitude to our speaker. With this, we end our speaker session. I request everyone to kindly be seated. The valedictory function will start shortly. Thank you.
We shall be starting the valedictory function within a few minutes, 2-3 minutes. So just we'll be arranging a dais. So be patient and be seated. VC sir also will be coming soon.
सर बंद करना है।
चार्जिंग दे
53 है।
ठीक है चलिए
Yes. शाश्वत करें ना पहले जैसे कुछ होना अरे मेरा नहीं पता उससे पूछ रहा है कि मतलब भी कर रहे हो ना कह रहा है पहले कर रहा हूँ सर उसका क्या तुम्हारे पहले कौन सा पूछा क्या नाम क्या वो भी कर रहा है उसमें क्या वो फोटो अपलोड होती ही नहीं है दूसरा बंदा नहीं करता
देखो ऐसा लग रहा है कि फाइनल नहीं डाटा के लिए मैं रेडी
सेकंड को है कुछ कैश प्राइस है प्रोसेस और तो वही समझता है वो डायलर 30 के ना कैश
नहीं है
30 नहीं पता चला
वो ओवरऑल सब इवेंट
वो 3,000
ये मिलेगा बहुत ज़्यादा मिलेगा ये हाँ रुद्र हेलो हाँ बोलो हाँ सर बताइए गुड इवनिंग सर अभी वैलिडिटी सेशन शुरू होने वाला बताइए अभी बाहर है जस्ट अभी सर अभी शूट नहीं हो पाएगा क्योंकि वैलिडिटी में फ़ोन लगे हुए हैं ना पूरे हाँ सर अभी शुरू हुआ है और ये चलेगा 1 घंटा क्योंकि अभी से वो टीम को अवार्ड मिलेंगे अभी वीसी सर का होगा वीसी सर को मिलेगा मतलब सबको ऐसा होगा ना लाइन में अभी
पेपर लगवाना है
The curriculum of all programs offered by the university is in line with the evolving global world and state of the art to meet the future requirements of industry and society and in line with the NEP. One of the major features of these programs is multiple exit, provision of minor degrees. Recently, the university has recruited 44 new faculty members having very good academic and research credentials, having qualifications from IITs, IITs and foreign universities.
अरे वो राइट
The Department of Computer Science and Engineering was established in 1984 with a 4-year BTech program with an intake of 30 students. The BTech Information Technology program was introduced in the year 2000.
Good evening, everyone. An inception of the dream, a step towards progress, and a landmark moment we all have been witnessing since the past 3 days. Crucial as the event is, we are thrilled to embark on this journey together. I wholeheartedly welcome you all to the valedictory function of Chem-Technova 2026. As we commence this momentous occasion, it is our honor to invite our distinguished guest onto the dais. May I kindly request Dr. S.V.A.R. Shastri Sir, Professor G.L. Devnani Sir, Dr. Rajesh Garg Sir, Professor Seema Paroha Madam, Professor Rajneesh Kumar Sir, and Honorable Vice Chancellor Professor Samsher Sir to take their seats on the dais. Thank you, Madam and Sirs. As we continue this auspicious event, it is our privilege to extend a warm and heartfelt welcome to the distinguished personalities who have honored us with their Ladies and gentlemen, it is now my great honor to invite the organizing secretary of the event, Dr. S.V.A.R. Shastri sir, to deliver a brief report of Chem-Technova 2026. Sir has been instrumental in bringing this event together and is a respected figure in our field. His leadership and dedication have set the stage for what promises to be an insightful and inspiring gathering. Please join me in welcoming Sir to the podium.
Thank you. Respected Chief Guest, Professor Shamsher sir, Honorable Vice Chancellor of HBTU Kanpur. Guest of Honors, Professor Rajesh Kumar sir, Head School of Sustainability, IIT Madras. And Guest of Honor, Professor Seema Paraho Madam, Director, NSA Kanpur. Distinguished guest, Dr. Rajesh Redji, Chairman of IIChe Kanpur Regional Center. HOD Chemical Engineering, Professor G.L. Devnani sir. Resource persons, faculty members, scientists, industry participants and dear delegates, online and offline mode both. We once again welcome you all to the valedictory function of the 4th edition of the 3-day international conference, Chem-Technova 2026, organized by IIChe Student Chapter, Department of Chemical Engineering, School of Chemical Technology, HBTU Kanpur, and the School of Sustainability, IIT Madras. Conference theme was Circular Economy in Chemical and Environmental Systems, Challenges and Strategies for Achieving Sustainable Development Goals. So there were 4 plenary lectures, 8 keynote lectures, 10 invited lectures given by eminent speakers across India and the world. There were 2 cultural evenings on the first and second day. About 400 papers were presented in this international conference in around 20 parallel sessions, which were held both in online and offline mode. And the participants were from US, UAE, UK, Spain, Chile, Brunei, France, Australia, Nepal, and India. So there are total 30 awards which will be given to the participants today in this function, based on the best paper presentations and poster presentations. So these are sponsored by Cisco Energy Systems and Dhunsari Petrochemicals with the cash prizes, and it will be given to the best paper and poster awardees. I thank all the sponsors for supporting us in organization of this international conference. The student team of IIChe Student Chapter of our university has worked very tirelessly in the last 10 days, especially for making this event a grand success. I thank the Honorable Vice Chancellor Sir, HBTU Kanpur, for always encouraging us to work for the benefit of the students and the university. Special thanks to Professor Seema Paraho Madam, Director NSA Kanpur, and Dr. Rajesh Garg Sir for gracing the occasion. Special thanks to Professor Rajneesh Kumar Sir, Head School of Sustainability, IIT Madras, for co-organizing this conference. They have accepted to associate with us also in the 5th edition of the Chem-Technova, which will be happening in next year, 11th to 13th March 2027, in a much bigger and grander way. We have tried to put our best efforts in organization of this conference. However, if there are some inadequacies or inadvertent mistakes from our side, please do forgive us. Looking forward to serve all of you again in the 5th edition of Chem-Technova 2027 next year during 11th to 13th March. Namaste and Jai Hind. Thank you.
Thank you, sir, for your warm and insightful address. Ladies and gentlemen, it is now the time to introduce the special guest of the event, Dr. Rajesh Garg sir, Chairman IIChe Kanpur Regional Center. To give you all a brief introduction to his illustrious career, I would like to invite Ms. Tanishka Trivedi to the podium.
Thank you, Apurva. It is my pleasure to introduce our special guest, Dr. Rajesh Kumar Garg sir, an accomplished chemical engineer, academician, and industry professional. Dr. Garg sir completed his B.Tech in chemical engineering in 1981 and M.Tech in plastics engineering in 1983, and later pursued several other qualifications including LLB, MBA, MCA, and a PhD in chemical technology. His research work includes studies on polymer systems such as LDPE, LLDPE, and HDPE blends, and grafting reactions in rubber, and reflecting his strong contribution to polymer science and chemical engineering. Alongside his academic achievements, he has made significant contributions to industry. He promoted Garg Polymers in 1986 for manufacturing polymer films and recycling plastic waste, and has been managing Garg gas service in Kanpur since 1983, serving thousands of domestic and industrial consumers. He has also contributed to education, serving as the director of Prabhat Engineering College, Kanpur Dehat, from 2012 to 2016, and currently works as a CEO of Garg Consultancy Services. Dr. Garg sir is a life member of Indian Institute of Chemical Engineers and a fellow of the Institution of Engineers India, highlighting his respected position in the engineering community. With his vast experience in both academia and industry, we are truly honored to have him with us today. I warmly welcome Dr. Rajesh Kumar Garg sir and invite him to share his valuable insights with us.
Good evening, everybody. I am Dr. Rajesh Kumar Garg, passed BTech in 1981. Then I continued further. 1983, I completed my M.Tech in Plastic Technology. You will be glad to know that I have got advantage of startup in that years, 81, 83, while our government is focusing on startups, industries, trades. I have got all achievement from my individual degree. जैसे first chemical engineering, I was being selected in Hindustan Petroleum as a unemployed engineering graduate dealer distributor for Kanpur area. That is only for engineers. While normally sometimes graduate या open category there are things, but I have done work like officers of Hindustan Petroleum and then completed our agency 40 years. Now after that some time I started my plastic industry, Garg Polymers, and we were producing polythene films, polypropylene films and high molecular high density polyethylene. We have taken material from IIChe till Polyolefins Industries Limited. At the same time, we have supplied to defense sector like Ordnance Equipment Factory, Ordnance Parachute Factory, Hatkarga, UP State Textile Corporation, etc. We have got advantage of education in every sector because at that time in the 85, 90s, 87 onwards, there was a system developed by UP government that new unit will get 5 years sale tax exemption. That was very difficult at that time, but due to good studies and continuous education sector, I have done that thing and we got the sale tax exemption. Then we started our Kriti Polychem Private Limited because my BTech was in chemical engineering or M.Tech and further PhD Tech plastics. I have made blends. My research topic was 3 ternary blends for extruded applications. That I have done up to 99. While HBTU is the most good place for me, although I used to go to DMSRD lab, IIT lab, CSJMU that time also, but I am mainly touched in the HBTU and engineering sector. Presently, I am the chairman of Indian Institute of Chemical Engineers and students chapters. Whatever we are trying, that our building, our system will be developed. We are in contact with the higher authorities. BC sir is very kind to us and our applications have been forwarded. And further, in any case, my expertise is now, because at that time also startup for ordinary persons, MSME, micro, small, medium enterprises में mostly students अभी चाहेंगे कि हमको इंडस्ट्री लगाए तो उनके लिए बहुत बड़ा हवा सा लगेगा भाई मेरे लिए बड़ा इजी काम रहा, क्योंकि हमने फेल्योर से सक्सेस का रास्ता बनाया, स्टेपिंग स्टोन फॉर सक्सेस हमने इंडस्ट्री में अपने व्यवहार से। अच्छा, इसके लिए हमारी एजुकेशन का मिडिल पार्ट में रखा। हाई स्कूल में दीनदयाल उपाध्याय से पढ़ा हूँ कानपुर के, तो मेरी तो संस्कृत में भी डिस्टिंक्शन रही है, मैथमेटिक्स और फिजिक्स। तो मैं इस चीज का एडवांटेज जो मिलता था, किसी को भी इंट्रोड्यूस कर रहे हैं। आज हमारी, मैंने काट दिया सर को, तो होते होते 12 डिग्री, मतलब बीटेक केमिकल, एमटेक प्लास्टिक, एलएलबी, पीएचडी, एमबीए, एमसीए, 5 सब्जेक्ट एमए के बाद एलएलएम में कर चुका हूँ। तो माय फादर वाज एडवोकेट, माय सिस्टर रजनी अग्रवाल इज आल्सो एडवोकेट एंड एलएलएम। उनसे भी प्रेरणा लेके, चाहे मुझसे वी आर 3 ब्रदर्स एंड 2 सिस्टर्स। इस चीज को जान के आपको खुशी होगी कि टेक्नोलॉजी में हम लोग कैसे, मेरा सबसे छोटा भाई, 3 भाई में बड़े ब्रदर अलग पैकेजिंग इंडस्ट्री बहुत स्ट्रगल करके पेपर मिल, ये सब चीज भी लगाई, अभी भी एडहेसिव इंडस्ट्री। मैं तो ट्रेडर भी हूँ, सबकी एसोसिएशन में भी हूँ। बहुत बड़ा हमारा कानपुर लेवल पर 1800 गज में एंटरप्राइज है और कंसल्टेंसी सर्विस के साथ हम लोग अवेलेबल हैं। आप में से कोई भी होता है जिनको इंडस्ट्री लगानी, हमारा वो जाता है, तो सोलर के हमने दे रखे और इंडस्ट्रीज को किराए पे भी दे रखा, ट्रेड एंड इनको। और सबसे खास बात कि मेरा छोटे भाई की हवाई जहाज कंपनी, इट इज इन द नेम ऑफ गर्ग एविएशन लिमिटेड, एंड वी आर हैविंग आवर ओन 50 planes, 5 planes 2-seater Cessna, 5 planes 6-7 seaters, and we also do maintenance for HAL company also. So in that time, mostly the atmosphere was not good, but practical. I can say that we are doing much better in the real ground sector. वर्कशॉप के टाइम में हम लोग 70 डेज जो वर्कशॉप अपनी, हम लोग सभी चीजें कारपेंट्री से लेके वेल्डिंग, मशीनिंग, सब पे हम लोगों ने काम किया, तो कॉन्फिडेंस लेवल है। और जब मैं प्रभात इंजीनियरिंग कॉलेज का डायरेक्टर रहा था, तो वहाँ पे भी खास तौर से ये देखा गया, तो वर्कशॉप बनी, लेकिन उतना इच्छा शक्ति के साथ नहीं तैयार होते। मतलब अभी के तो स्टूडेंट्स पास आउट होते हैं इंजीनियरिंग में, तो अगर वो और जोर लगाए, देखें किसी चीज़ की प्रॉब्लम तो आगे बढ़ सकते हैं। अब दूसरा चीज मैं बताता हूँ कि मैं इंडस्ट्री एसोसिएशन का, ये इंडियन इंडस्ट्री एसोसिएशन लघु उद्योग पार्टी नेशनल लेवल पे, फेडरेशन ऑफ इंडियन इंडस्ट्री ट्रेड सबसे जुड़ा हूँ। तो जो हम लोग टाइम निकालते हैं अभी हमारी आगे के लिए, मेरा बेटा देखिए, मेरी बड़ी बेटी ज्वेलरी डिजाइनर, डूइंग हर बुटीक एंड दिस कृति क्यूरियोसिटी ज्वेल्स, while my second daughter is Dr. Kavya Gar, has done MBBS and MS, and she is surgeon at Tata Varanasi, so doing cancer operations. So second enterprise. Third, my son is also engineer, BTech from UPES and America में 4 साल से है, 1921 से गया और बहुत अच्छा परफॉर्म भी कर रहे हैं। 96% नंबर थे। मतलब ये कहना चाहेंगे कि जो गैर में कभी कम्युनिकेशन का, हम लोग ढाई में 60-70% आने मुश्किल होते थे, तो लेकिन जो भी लगे गए, तो हर समय हमें ये देखना है कि हम कैसे आगे बढ़े। और किसी को भी कानपुर लेवल पे या कोई स्टेट लेवल पे भी दिक्कत हो, कोई अपनी इंडस्ट्री लगाना चाहे, तो हम तो शास्त्री जी को खास तौर से कह के रखेंगे कि इस तरह का हो। ट्रायल के तौर पे भी इंडस्ट्रीज, मेरे फादर इन लोगों की बहुत बड़ी इंडस्ट्री, सोचिए वो भी HBTI के, वो 61 बैच पास आउट, मैं 81 बैच भी थे, तो वो 63 बैच एमटेक और मैं 83 बैच, वो 69 में PhD करके, इतनी बड़ी इंडस्ट्री है। मतलब कितने टन्स का, उनको ऑल इंडिया HPCL को 25% का ग्रीस बनाने का है। अभी वो मतलब रियली टेक्नोलॉजी पर्सन, केमिकल बिजली आती थी, अब तो उनकी 70 मतलब 2014 में डेथ हुई, लेकिन उनको फिर हमारे साले साहब ने बहुत टेक्निकल, वो यहाँ से PhD कर रहे थे, लेकिन उस समय कुछ ये रहा होगा कि टाइम नहीं मिल पाया बाद में, नहीं तो अभी भी बहुत सेकेंड थर्ड जनरेशन काम कर रही है। तो मतलब हम लोग तो लोकल लेवल पे अवेलेबल ही है, और HBTI के लिए तो कभी भी कुछ भी होगा हम आते जाते रहेंगे। धन्यवाद. Thanks.
Thank you, sir, for your wonderful address. It is indeed a privilege to acknowledge the gracious presence of our guest of honor, Professor Seema Paroha Madam, Director, National Sugar Institute, Kanpur. And to introduce her, I would like to invite Ms. Nandini Chaudhary to the podium.
Thank you, Apurva. Professor Seema Paroha ma'am is the director of the National Sugar Institute, Kanpur, and a distinguished academician and researcher with over 25 years of experience in teaching, research, and industry consultancy. She has published more than 120 research papers in national and international journals and has successfully supervised 7 PhD, 2 MPhil, and 35 MSc students with several scholars currently pursuing doctoral research under her guidance. Her research focuses on alcoholic fermentation, bioethanol production from alternative feedstocks, value addition, and sustainable waste management practices for the distillery industry. Since joining the National Sugar Institute as professor through UPSC, she has completed over 10 externally funded research projects leading to impactful publication and patents. Professor Paroha ma'am also serves as chairperson of the Expert Committee on Sugar Standards and the Sectional Committee on Sugar at the Bureau of Indian Standards and contribute as a technical expert to multiple national committees related to sugar, food and bioenergy sector. She has received several prestigious awards including the IIChe Gold Medal at STAI Convention 2014 and the Sugar, Ethanol and Bioenergy International Award SEIA 2025. Now, I kindly request ma'am to please address the gathering.
Thank you very much for an elaborative description. Good evening, everyone. Dignitaries on the dais, off the dais, my dear students. Today, at the end of the valedictory function, I am here with immense pleasure to be present here in the Chem-Technova 2026, a wonderful platform that has brought together brilliant minds and academia, industry and research institution together. This conference, I suppose, has been successfully created an environment for exchanging ideas, innovations and technological advancement in chemical and environmental engineering. As highlighted in the conference theme, the focus that is on circular economy in chemical and environmental system for sustainable development goal is both timely as well as extremely relevant for the future of our industry as well as for environment. We have witnessed insightful keynote lectures, technical presentations, panel discussions and innovative ideas from young researchers and professionals. Such events play a vital role in the encouraging innovation, strengthening collaboration between academia and industry, and nurturing the next generation which is sitting in front of us as of scientists and engineers. I congratulate the organizing committee of Harcourt Butler Technical University, what you call as chemical engineer student, and all the volunteers for their dedication and hard work in organizing this successful event. My sincere appreciation also goes to the speakers, participants, sponsors who contributed to making this conference meaningful and impactful. I would also like to congratulate the prize winners and the participants who presented their research posters and innovative ideas. Your enthusiasm and creativity are the driving force for the technological progress. Institutions like National Sugar Institute Kanpur and HBTU Kanpur share a common vision of promoting scientific excellence and sustainable industrial development. I hope the discussion and the knowledge shared during the conference will inspire new collaborations, research and initiatives, and practical solutions for the challenges faced by our industry and the environment. With this word, I extend my heartfelt congratulations to the organizers and participants once again. I wish you all a great success in all your future endeavors. Finally, I express my appreciation to everyone who contributed to the success of this conference. May the knowledge shared here inspires continued research, innovation, and collaboration in the years ahead. Thank you, and I wish you all a very best for your future. Thank you very much.
Thank you, madam. It is a matter of great honor and privilege to acknowledge the gracious presence of our guest of honor, Professor Rajneesh Kumar Sir, Head School of Sustainability, IIT Madras. And to introduce him, I would like to invite Ms. Tanishka Trivedi to the podium.
Thank you, Apurva. Professor Rajneesh Kumar Sir, FNE, is a professor in the Department of Chemical Engineering at IIT Madras. He is currently head of the School of Sustainability at IIT Madras. He is also a board member of Energy Consortium, which is a consortium of 14 industries collaborating on net zero technologies with IIT Madras. In past, he has served as senior scientist at CSIR NCL Pune and research associate at National Research Council, Canada. His PhD is from the University of British Columbia, Canada, a master's from Indian Institute of Science, Bangalore. He has research interest in carbon dioxide capture and sequestration, unconventional energies, process development, and scale-up. Sir is a recipient of Shanti Swarup Bhatnagar Award in Engineering Sciences 2022. Sir is also a recipient of NASI Scopus Young Scientist Award in Chemistry for the year 2016. He was recognized as highly cited researcher in the year 2018. In 2020, Sir received Dr. YBG Verma Award for Excellence in Chemical Engineering Teaching. I warmly welcome Professor Rajneesh Kumar Sir and invite him to share his valuable insights with us.
Without slides, I don't talk a lot actually, so I would rather keep quiet. And I always believe that I am a teacher, I am not a preacher, so I don't preach anything. Whatever I teach, I will teach based on the technical content which I have in my slides. So today I am not going to talk much. However, I will, based on whatever we have discussed before in my technical session, I basically am going to talk about sustainability a little bit more. If you believe United Nations Sustainability Goal between 1 to 17, there are 3 components in there: environment, social and governance. Whatever we talked about in last 1 hour or so, we have mostly covered environment part. Engineers don't understand social and governance component well. I would basically request every one of you to understand the social and the governance part of ESG, unless and until you basically understand it, because the most of the job opportunities in future is going to be there in the social and the governance part. So if you really want to be a good engineer, other than technical knowledge, you should also understand the social and the governance part of it. So with that, let me stop this discussion. Thanks.
Thank you, sir. It is a moment of great pride and honor to acknowledge the gracious presence of our chief guest Honorable Vice Chancellor, High Court, Technical University, Kanpur, Professor Samsher Sir. To give us an introduction to the illustrious career of Sir, I would like to invite Ms. Siddhi Gupta to the podium.
Thank you, Apurva. Professor Samsher Sir is presently serving as Honorable Vice Chancellor HBTU Kanpur since April 20, 2021. He has also served as Honorable Vice Chancellor Bundelkhand University, Jhansi. Honorable Vice Chancellor Sir is Professor in his parent department, that is Department of Mechanical Engineering, Delhi Technological University, DTU. During his tenure in DTU, he has also held several administrative portfolios such as Registrar, Controller of Finance, Dean Student Welfare, Dean Continuing Education, Head of Department of Mechanical Engineering, Proctor, and being associated with several other academic and administrative committees. He has also worked as a director in the National Institute of Electronics and Information Technology, Delhi, and looked after its regional offices in Gorakhpur, Lucknow, Patna, Chandigarh, Ajmer, Shimla, Ropur, and Delhi. He has also worked as professor in NIT Jalandhar, Punjab, DY Director or Assistant Director in National Powertrain Institute NPTI, Faridabad, Haryana, Engineer in NTPC, New Delhi. During his tenure at NPTI, he was involved with a prestigious project titled Development of Computer-Based Training Packages for Power Sector in India, funded by the United Kingdom and visited United Kingdom as part of the same. He holds a bachelor's degree from HBTU Kanpur, MTech and PhD from IIT Delhi, and MBA from DTU Delhi. Honorable Vice Chancellor Sir has more than 120 research papers in national and international journals or conferences of repute to his credit. He has supervised 12 PhDs and 17 MTech students, and many doctoral students are pursuing their studies. He has authored 2 textbooks and 3 edited books and developed 3 computer-based multimedia packages. He has also completed sponsored research projects from several government or private funding agencies. He is fellow member of the Institution of Engineers, member ISME and member ISTE. During his association with NPTI, Honorable Vice Chancellor Sir received the Consistency High Performance Award and the Scroll of Honor Award in NPTI. He was also awarded the Best Research Paper Award by the Institution of Engineers India, Commendable Research Award by DTU. So now I would be pleased to call our Honorable Vice VC Sir to address the gathering.
Respected Professor Seema Parwar, Director of NSI Kanpur, Professor Rajneesh Kumar from IIT Madras, Dr. Rajesh Garg, our own alumni and Chairman of IIChe chapter, Professor G.L. Devani, the Head of the Department of Chemical Engineering, Professor Shastri, the Honorary Secretary, our Dean, HODs of the University, faculty members, distinguished keynote speakers, delegates from different countries, eminent scientists, and dear scholars and students. Good evening, all of you. It gives me immense pleasure to be here with you today at the valedictory session of 3 days international conference Chem-Technova 2026. Over the past 3 days, this conference has truly reflected the spirit of scientific curiosity, intellectual exchange, and global collaboration. I congratulate the organizing committee, participating institutions, and all delegates who contributed to make this conference meaningful and successful. During these 3 days, we have witnessed stimulating keynote lectures, insightful technical sessions, and vibrant discussions covering emerging areas of chemical science, chemical engineering, sustainable materials, green technologies, and innovative industrial processes. These discussions remind us that chemistry and chemical technologies are at the heart of modern civilization, from pharmaceuticals and clean energy to advanced materials and environmental protections. However, beyond the technical sessions and research presentation, this conference has also demonstrated the power of togetherness. When scholars, scientists and students from diverse regions and disciplines come together with a shared purpose, knowledge multiplies. Innovation rarely emerges in isolation. It grows in an environment where ideas interact freely. Conferences like this, Chem-Technova provides such a platform where collaboration becomes stronger than competition and collective wisdom becomes more powerful than individual efforts. In today's rapidly changing technological world, interdisciplinary collaboration is becoming increasingly important. The solution to global challenges such as climate change, energy sustainability, water purification, and green manufacturing requires the integration of chemistry and engineering, biotechnology, data science, and artificial intelligence. When we work together across disciplines and cross borders, we create opportunities for transformative innovations that can benefit humanity. At the same time, scientific advancement must always be guided by integrity and ethical responsibility. Research is not merely about publishing papers or achieving technological breakthrough. It is about seeking truth, maintaining honesty in the experimentation and reporting, and ensuring that our innovations serve society responsibly. Integrity is the foundation of credible science. Without integrity, even the most sophisticated technology loses its value. Equally important are the human values that guide our professional and personal lives. Respect for others' ideas, openness to new perspectives, humility in learning, and commitment to the welfare of the society are essential qualities of a true scientist. As a researcher and educators, we must ensure that our work contributes not only to technological progress, but also to the betterment of humanity. Another important lesson from this conference is the importance of teamwork. Modern scientific challenges are complex and cannot be solved by a single individual working alone. Breakthrough discoveries often emerge from the team that bring together diverse expertise, chemists, engineers, biologists, physicists, and data scientists working with a shared vision. Effective teamwork requires trust, mutual respect, and willingness to learn from one another. For the young researchers and students who participated in this conference, I would like to emphasize that teamwork is not just about the working together, it is about growing together. When you collaborate, you expand your thinking, develop new skills, and learn to appreciate the strength of others. These qualities will definitely define your success not only as a scientist, but also as responsible citizens of India. As we conclude this conference, I hope the discussion initiated here will continue beyond these 3 days. Let the idea exchange here evolve into joint research projects, collaborative publications, faculty exchange, and large-term international partnership. The true success of conference is measured not only by the sessions conducted, by the collaboration it inspired the future. I would also like to appreciate the dedication of organizing committee, coordinators, volunteers, and supporting staff who worked tirelessly to ensure the smooth conduct of this conference. Organizing an international conference requires careful planning, teamwork, and commitment, and your efforts have been truly commendable. Before I conclude, let me share a simple thought. Science progresses the fastest when knowledge is shared, integrity is maintained, and people work together with a common purpose. If we continue to uphold these principles, togetherness, integrity, human values, and teamwork, then the scientific community will not only achieve technological excellence, but also contribute meaningful to a sustainable and equitable world. I will once again thanks all the distinguished speakers, delegates, researchers, and students for their valuable participation in Chem-Technova 2026. I wish you all the great success in your future research endeavor and hope that the relationship and ideas developed during this conference will lead to many impactful innovations in the years to come. With these words, I declare the International Conference Chem-Technova successfully concluded. I thank you all. I wish you a safe journey back to your destination. Thank you very much. Jai Hind.
Thank you, sir, for your wonderful address. You are truly an inspiration for the university. It is now the time to felicitate our esteemed dignitaries for their valuable presence today. I kindly request Head of Department of Chemical Engineering, Professor G.L. Devnani, sir, and Organizing Secretary, Dr. Shastri, sir, to felicitate the Honorable Vice Chancellor, sir. Thank you, sirs. I kindly request Dr. G.L. Devnani, sir, Dr. Shastri, sir, and Professor Rathore, sir, to felicitate Professor Rajneesh Kumar, sir. Thank you, sirs. I also request them to felicitate Professor Seema Paroha, madam. I request to felicitate Dr. Rajesh Garg, sir. I kindly request Honorable Vice Chancellor Sir to felicitate Professor G.L. Devnani Sir, Head of Department of Chemical Engineering. I again request Sir to felicitate Dr. S.V.A.R. Shastri Sir, the organizing secretary of the event. Behind every successful event, there are dedicated mentors who guide, inspire, and support us at every step. Today, we take a moment to express our heartfelt gratitude to our faculty coordinators whose constant encouragement and invaluable guidance make this event possible. I kindly request Honorable Vice Chancellor Sir to felicitate our faculty coordinators. Dr. Omkar Kushwaha Sir from IIT Madras. I request to felicitate Dr. Shravan Kumar Sir. I request to felicitate Dr. Pranav Chaudhary Sir. I request to felicitate Dr. Zeenat Arif Madam. I request to felicitate Dr. Binita Singh Madam. I request to felicitate Dr. Abhishek sir. Thank you, sirs. Every successful event is the result of dedication, teamwork, and tireless effort among those who have worked relentlessly behind the scenes are the IIChe student chapter team, whose leadership, commitment, and enthusiasm have played a vital role in making this event possible. I kindly request Professor G.L. Devnani sir and Dr. Shastri sir to felicitate the core team of IIChe student chapter. I also request Honorable Vice Chancellor sir to felicitate the IIChe student chapter team, starting with Mr. Vishwajit Yadav sir, Secretary. Mr. Charan Upadhyay sir, Coordinator and Treasurer. Mr. Yash Kumar Shakya sir, Operations Head. Miss Dona Srivastav, Joint Secretary. Mr. Kushag Bajpai, Joint Secretary. Mr. Akshat Srivastav, Joint Secretary. Now I would request to felicitate our executive committee members, Miss Anshika. Miss Swati. I would request to felicitate Miss Meenakshi Verma. Miss Anushka Mishra. Now I would request to felicitate our executive subcommittee member, Mr. Akarshan Pandey. Mr. Ansh Shukla. Miss Agni Sharma. Mr. Divyansh Krishna. Mr. Suryansh Sabu.
Mr. Uday Taneja. Miss Apurva Mishra. Miss Astha Kushwaha.
Mr. Sachin Gupta. Miss Vaishnavi Singh. Mr. Sparsh Gupta. Miss Akanksha Mishra. Miss Kanishka Mishra. Mr. Sanskar Shukla. Mr. Pushkar Nishad. Miss Shreya Pandey. Mr. Pranjal Gupta. Mr. Vaibhav Yadav. Miss Garima Sagar. Mr. Pravan Gupta. Thank you, sirs. Now we will felicitate the winners of oral and poster presentations. For poster presentation, which held in New Audi, first session, which started from 10 a.m. to 11:30 a.m., the first prize goes to Anmol Pandey from IIT Kharagpur. Second prize goes to K. Vamshi Krishna Gaur from Manipal Institute of Technology. For the second session of poster presentation, which started from 11:30 a.m. and finished at 1:30 p.m., the first prize goes to Devyani Sengar from Agharka Research Institute. The second prize goes to Ms. Vaishnavi Singh, Mr. Divyansh Krishna and Mr. Suryansh Sahu from HBTU Kanpur. winners of oral presentation morning session which started from 10 a.m. and finished at 1:30 p.m. For LHC 102, the first prize goes to Amit Yadav from the Department of Physics, HBTU. The second prize goes to Rani Yadav from HBTU Kanpur. For LHC 103, the first prize goes to Bhanu Pratap Singh from NIT Warangal. The second prize goes to Ishika Jaiswal from HBTU Kanpur. LHC 104, the first prize goes to Saksham Ghimere from IIT Madras. The second prize goes to Sumaya Fatima from HBTU. LHC 105. The first prize goes to Dr. Vivek Kumar, RGIPT Jazz. The second prize goes to Dr. Pooja Thakur from NIT Hamirpur. For oral presentation afternoon sessions, LHC 102, the first prize goes to J. Prathosh Iyer from Shiv Nadar University, Delhi. The second prize goes to Unnayan Srivastav, HBTU Kanpur.
For LHC 103, the first prize goes to Pooja Singh from HBTU Kanpur. to Apurva Mishra from HBTU Kanpur. For NHC 104, the first prize goes to Vishwas V. Deshpande, former Assistant VP Reliance Industries.
The second prize goes to Swati Patel, HBTU. NHC 105, the first prize goes to Solomon Thomas, CEO, Cochin Aqua Purifiers. The second prize goes to Ajit Tiwari from HBTU Kanpur. With this we end the offline sessions. Now the winner of online sessions, session 1. The first prize goes to N. Muthulakshmi Odal, Government College, Coimbatore, Tamil Nadu. Second prize goes to Prathish T. from SSN College of Engineering, Chennai, Tamil Nadu. For online session 2, the first prize goes to Dr. Vishnu Priyan V. from IIT Madras. Second prize goes to Suyash Joshi from HBTU Kanpur. For online session 3, the first prize goes to Kishore Kumar Sambhagi from University of Chile. And the second prize goes to Acharya Arvind Kumar Girish Kumar from Ganpat University, Gujarat. For online session 4, the first prize goes to Dr. Ravindra Kumar Gupta, King Saud University, Saudi Arabia. Second prize goes to Sonali Bhatnagar from Dayal Bagh Educational Institute. For online session 5, the first prize goes to Dr. Monal Datta from Haldia Institute of Technology, West Bengal. And second prize goes to Haripriya Veer Kumar from SSN College of Engineering, Chennai, Tamil Nadu. With this, we finish all the winners. I kindly request the dignitaries to please take their seats. As participants are the heart of any event, their feedback truly matters to us. So, I would like to invite participants to share their experience of the conference with us. Anyone among the participants who would like to share their experience can please come to the podium. Anyone please?
Dignitaries on the dais, and viewers and participants of the dais. I am Solomon Thomas, coming from Cochin, CEO of Cochin Corporations. A very program, prestigious,
meetings, conference. The feedback is good for future as well as any flaws or anything happen in the past. I'm just telling you quite a few points, just frankly from my heart. Whether it is like or not, I don't worry much. Because I am also conducting several programs like this. So we are inviting audience to get the real feedback. Could you please raise your hand those who are coming from the industrial segment? This industrial segment. Anybody? One reliance for somebody else this? No. Yeah. Okay. No problem. So I am directly from the industrial segment. I am a chemistry graduate in 1983. Then after MSc, then I got the MBA. I am a water treatment plant designer. So what you just see from this room, just see this room, this hall, or in your car, in your office, or in your residence, how many products are Indian made? Even fact, we have to think ourselves. It's not for blame anybody. Please don't misunderstand. Yesterday, here there was around 270 papers, right? Very sorry for here. Around 300 papers. Last year also, I think almost same. Next year also, definitely more than that. In our universities, I am coming from Kerala. Our every universities, every year, n numbers of theses, doctorates, PhDs are coming, keeping in the Alamara. Now it's not in the Alamara, it's in the pendulum. But if you see these products which are here in China, it's coming from China, in our house, office, car, everything, very user-friendly, very cheap. No thesis made for that, behind that product. No any PhD, no doctorate, no any research scholars are coming from that. We have to think in that. While we are making a thesis or preparation or our findings, see the technology. How do you find the technology is best? The technology is best when it is compared to the competitor's price. Otherwise, there is no use. It is for getting your degree, getting your doctorate, getting your ETC scale, salary, your promotion, these are things. India is facing, this is one of the big problems. This is not transferred to the industry. Scholars are here. Even if transferred, it is not economical. So I request you, sir, please see your thesis yesterday and last year also. How many of them transformed to the industry? And how many industrials are here? If it is transformed to industry, whether it is cost effective or not. If it is not cost effective, what is the use of these whole functions? I am not blaming, it's a great thing. First time in my life, I am seeing this much doctors are in a single auditorium, in PhD doctors. So thanks a lot, sir, once again. Definitely, I am very much interested to associate with you in future also. Just on small words, I presented two things yesterday. It's from my own finding. One is for Indian Railway. Have you anybody gone to Indian Railway more than 24 hours or 30 hours? Today, you are facing a big problem. You cannot sit inside. We are sitting like in a safety tank. Technology is increased. Technology is shooting like, but we are trailing behind. You cannot sit like closing your nose. I invented a product and presented yesterday. I don't know how many of them saw that. While train is traveling, using the air up to 60 km per hour to 150 km per hour, free air we are getting without losing the friction loss. Treating that septic tank or the anaerobic digester by using the free air, recycling the water using back to the railway complex. That's one invention I got. Without any electricity, without any cost, eco-friendly. That's sustainable. Second, I presented yesterday. You are drinking n numbers of drinking water bottles are there. You are drinking the water only because of the belief. Whether microbes are there or not, you cannot. You are drinking water from the water authority from the water supply, from the aqua purifier, everywhere. But you cannot test that. You can test your chemical engineers. You can test your all waters, address, color, disorder, temperature, everything by electronic devices. But microbes, no. You have to take that water. You have to take in a bottle, sterile water, take to the lab, test. 3 days it will take 3,000 rupees. I will enter a system for 300 or 400 rupees. Going to launch in a small dabba, keep the water inside for 6 hours, you will see the collections. Why I am telling these things is not a place to reveal that the product which we are making is should be good for the public and economic health. These two things. So like that, I request you people, you are coming you become big industrial supporters in future. Your thinking, your way of thinking, whether efficient and effective and cost effective, there is no point in studying good things. Now the concrete survival of the fittest. There is no other philosophy. Now China is, we are 100 years behind China. Please think that. Thanks once again, thanks a lot, and giving me for this opportunity to talk to you. Thank you.
Thank you, sir. It is now my honor to invite Professor G.L. Devnani, sir. Sorry, I would request anyone else who would like to share their feedback.
अक्षत इधर इधर इधर
Respected Vice Chancellor, thanks to Shastri sir and Shravan sir for organizing such a grand festival again, Chem-Technova for gathering all of us here. And I have been a student from here only. 2018 I cleared my B.Tech degree from Department of Biochemical Engineering, School of Chemical Technology. Earlier it was School of Chemical Technology, means we used to get a degree of B.Tech in Chemical Technology with specialization in Biochemical Engineering. So we used to feel proud that also we are a part of chemical engineering. Majority of the subjects we used to share with chemical engineering only. So coming to the topic here, in this Chem-Technova, we used to get many things and we used to share many parts along with. And please, it's a request to all the biochemical engineers, don't feel like that we are something separated out of the world. We are a part of chemical engineering and we have to work in collaboration only. And thanks to Shastri sir and Shravan sir again, that they have organized a platform to share our knowledge. What all things we are having, we are sharing. And by sharing only we can proceed. Thank you.
Thank you, sir. Anyone else who would like to share their thoughts? It is now my honor to invite Professor G.L. Devnani, sir, the head of the Department of Chemical Engineering, to give concluding remarks for the event. Sir has been an exemplary leader in the field of chemical engineering, guiding both academic pursuits and research innovations within the department. His contributions continue to inspire students and faculty alike, and we are eager to hear his insights. Please join me in welcoming Sir to the podium.
Honorable Vice Chancellor, Professor Samsher sir, dignitaries on the dais, eminent speakers, faculty members, researchers, industry experts, participants, and my dear students. A very good evening to all of you. It is my privilege to offer the concluding remarks at the valedictory session of Chem-Technova 2026. Over the past 3 days, this conference has provided a meaningful platform for academic exchange, innovation, and collaboration. The deliberations, keynote talks, technical sessions, poster presentations, and discussions have clearly demonstrated the growing importance of chemical engineering in addressing sustainability, resource efficiency, environmental protection, and technological advancements. The theme of this conference has been highly relevant, and the wide range of topics presented has reflected the depth and diversity of current research in chemical and allied fields. It is encouraging to see participation from academia, industry, and research organizations because the challenges of the future can only be addressed through collective effort and interdisciplinary thinking. I sincerely thank all the distinguished speakers, session chairpersons, delegates, and participants for their valuable contribution. I also congratulate to all the presenters and award winners. Your work and enthusiasm have enriched this conference greatly. I would especially like to appreciate the efforts of organizing committee, faculty members, research scholars, student volunteers, and support staff. This dedication and hard work have made Chem-Technova 2026 a successful and memorable event. As we conclude this conference, let us carry forward the ideas, discussions, and collaborations initiated here. I am confident that the outcome of this gathering will inspire future research, innovations, and partnerships. On behalf of the Department of Chemical Engineering, HBTU Kanpur, I extend my heartfelt gratitude to everyone associated with Chem-Technova 2026. Thank you all.
Thank you, sir. Now we come to a very special moment of this conference, the official release of Chem-Technova 2027 brochure, which will mark another milestone in this remarkable journey. I kindly request dignitaries to release the brochure. Thank you, Madam and Sirs. As we are towards the conclusion of the event, I would like to invite Mr. Vishwajit Yadav Sir, Secretary IIChe Student Chapter, to deliver the vote of thanks.
Very good evening to everyone and all the dignitaries present on the dais. As we reach the conclusion of Chem-Technova 2026, it is my privilege to stand before you and express my heartfelt gratitude on behalf of the IIChe Student Chapter HBTU Kanpur. First and foremost, I would like to express our deepest gratitude to our respected organizers, Chief Patron Professor Samsheer Sir, Honorable Vice Chancellor HBTU Kanpur, Chairperson Professor J.L. Nani Sir, HOD Chemical Engineering, and our organizing secretary, Professor S.V.R. Sastry Sir. Your all's constant encouragement, guidance, and belief in students have been the backbone of this event. I would also like to sincerely thank all our distinguished speakers, guests, and experts who shared their invaluable knowledge and insights with us. A special word of gratitude goes to all our sponsors and supporting organizations. Your generous support and trust made it possible for us to organize an event of this scale. I would also like to thank the respected faculty members of the Department of Chemical Engineering at HBTU, our ex-HOD, Professor Ashish Kapoor Sir, Professor Ashwini Sood Sir, Professor Rajesh Katia Sir, Professor A.K. Rathore Sir, Professor Adarsh Arya Sir, Dr. Sheena Gautam Ma'am, Dr. Jeenidat Arif Ma'am, Dr. Vinita Singh Ma'am, Dr. Pranav Chaudhary Sir, Mr. Jirendra Kumar Sir, Dr. Amit Rathore Sir, Dr. D.B. Pal Sir, and Dr. Shraman Sir, for their continuous guidance and support. Your encouragement gave us the confidence to take on the challenges of organizing a conference like Chem-Technova. My heartfelt thank goes to all the participants, presenters and delegates who traveled from different places and contributed to their research, discussions and enthusiasm. Your participation truly gave life to the conference. And now I would like to acknowledge the entire organizing team and all volunteers. Behind every successful event lies a team that worked quietly, tirelessly and selflessly. Each member of this team dedicated countless hours, often working late nights, solving problems and ensuring that every detail was taken care of. The success of Chem-Technova 2026 is truly a reflection of their dedication and teamwork. On a personal note, this journey has been very close to my heart. I have been part of this chapter for several years, first as sub-executive member, then as joint secretary and now serving as the secretary. Throughout this journey, I have tried to contribute with sincerity, hard work and humility. I always did my best to support a collective effort and ensure that this event become a success. Seeing the team come together, support each other and turn an idea into reality has been one of the most rewarding experiences for me. Chem-Technova 2026 is not just an event. It is the result of dedication, collaboration and the shared passion of many individuals who believed in the power of knowledge and innovation. And finally, I extend my sincere thanks to everyone present here today. Your support, participation and encouragement made this event truly memorable. With immense gratitude and pride, I conclude my vote of thanks. Thank you all.
Thank you, sir. We deeply appreciate your efforts to make this event successful. Ladies and gentlemen, as we now approach the conclusion of this valedictory ceremony, let us take a moment to honor our nation by standing together for the national anthem. The anthem symbolizes our unity, pride and the shared values that bind us as a nation. I kindly request everyone to rise as we pay tribute to our country. Jai Hind. Thank you everyone. Please be seated. Ladies and gentlemen, we have now come to the group photo session, a wonderful way to capture the memories of today's event. For the first group photo, I would like to request the dignitaries to gather for the first group photo. For the second group photo, I kindly request all the faculty members to come along with our dignitaries. request all the IIChe student chapter members and the participants to gather for the final group photo. I request everyone, please come fast and stand nearby the stage for the group photo. I request the student chapter team to please come over the stage for the group photo and the participants to gather near the stage. Participants, please assemble near the stage. Kindly be quick, please. Thank you everyone. As we come to the end of this wonderful journey of Chem-Technova 2026, we extend our heartfelt gratitude to all the distinguished speakers, respected dignitaries, participants and organizers who make this conference truly memorable. With this, we conclude the conference on a note of gratitude and inspiration, hoping to see you all in another exciting edition of Chem-Technova in the coming year. Thank you.
चला जाए खत्म करो